Recall again that these three equations are the so-called Euler's equations for a free spinning rigid body. And what we want to do in this video is to solve these three equations of motion using MATLAB and see what the solutions look like. Okay. Um, okay. Here's essentially a MATLAB program that solves these three equations of motion. It's just a very straightforward ODE integration using ODE 45. We have um, omega xb, omega yb, omega zb, and then we have these three equations where I1 is Ixx, I2 is Iyy, I3 is Izz. Okay, these are just the same equations rearranged so that we have omega xb dot, omega yb dot, and omega zb dot computed in terms of these state variables. Okay, so all we're doing is integrating these omega equations. And of course, as we said, these equations correspond to moments equal to zero. If the moments were not equal to zero, really all we would have is plus m1, m2, m3 in the numerator. Actually, more specifically, it would be mxb, myb, and mzb. In other words, the moments on the rigid body, but represented in the body fixed frame. Okay, so that will actually be in the numerator, where the denominator is still these moments of inertia. Okay, so we just have three differential equations. Then we can solve them. So we're just clearing all the variables. We can either define the moments of inertia from scratch, or we can just use and then I2 is Iyy, and I3 is Izz. Okay, and we have lengths of the three sides of the cuboid A, B, and C, and these are the moments of inertia. We have a time range in which for which we want to simulate this system. We have some initial conditions for the body fixed, for the omega represented in the body fixed coordinates. We'll talk about that in a second. And here we are integrating the differential equations using ODE 45. And here we are just plotting t versus these omega xb, yb, and zb. Okay, pretty straightforward. Now, recall, actually, we can uncomment this thing. So if you run this thing, we have Ixx is 1.08, Iyy is 0.833, Izz is 0.41, which means that Iyy is the intermediate moment of inertia. It's the middle one, not because it's y, but because its value is between 1.08 and 0.4167. So what we expect from our discussions is that if, let's actually see what it looks like. So let's say we spin the object with some initial angular velocity that is essentially entirely around omega xb, and then not at all around yb and zb. In fact, let's make it completely along omega xb and then just run this and see what it looks like. Okay, this is what we get. Omega 1 or omega xb, yb, zb. So omega xb starts at 1, remains at 1 for all time. Omega yb remains at 0 for all time. Omega zb remains at 0 for all time. And this we know already because we know that if it starts rotating exactly along a principal axis, it will remain doing so forever, right? So that's something we just showed. What if we start very close to rotating about a principal axis, but not exactly? So in other words, it's mostly along xb, but then we just make up some relatively small um, angular velocity in the perpendicular directions. What does that look like? It looks almost the same. This looks really close to 1, um, and these look really close to 0, right? So they look pretty close to 0 still. Now what if we make it less close to 0 there? We see that this remains still relatively close to 1, and this sort of oscillates. Hopefully you can see the oscillations. Um, this seems to oscillate around 0, seems to oscillate around 0. Okay, we can increase this a bit more, something. These are just meant to be small numbers that is much smaller than this, so that the vector is mostly along this direction. Okay, so this remains basically at 1, and this has a bigger oscillation, but still oscillates around 0. So this is what we mean by when we say rotation about EXB is stable. In other words, if we give it a perturbation away from perfectly along EXB, the motion mostly remains almost along EXB, right? So it doesn't do anything dramatically different. Same thing for if you do an initial motion that is mostly along EZB, okay? So if you do an initial motion that's along EZB, then omega EZB mostly remains 1, omega YB and omega XB sort of oscillates about 0, remains small. The motion doesn't do something dramatically different from what it initially started out doing. But what about if the motion mostly was close to, so these negatives and positives I'm putting here don't mean anything. I'm just making them sort of generic. I could say something like times rand n or something like that, so that it's a random number. It's just meant to be a small number. Okay. Now we made it mostly along y, so let's see what this looks like. Okay, that's what it looks like, right? So y starts out at 1, remains at 1, remains at 1, remains at 1, and then becomes -1, then becomes 1 again, becomes -1 again, 1 again, and so on. XB, omega XB starts out at 0 and then becomes substantially non-zero and then goes to 0 again, substantially non-zero, goes to 0 again, and so on. So this is what we mean by unstable, right? So we start out rotating mostly about the y-axis, and then in this stage, instead of doing something pretty complicated, we'll see what's doing, and then it's rotating about the EYB axis again, but in the opposite direction, and then does something complicated, and then rotates about EYB direction, but in the anti-clockwise direction, and sort of it goes between clockwise and anti-clockwise about EYB, back and forth forever, right? So this situation persists forever. So this is what we mean by unstable, in that there are these very large changes in the motion compared to what it started out with. Okay. Um, so this is just plotting the omegas. What we would like ideally, like we discussed in the previous lecture, what we would like is to actually do an animation that describes this motion um, effectively. So let's do that. So here is the rotation matrix implementation of it. Um, so I guess we can do the same kinds of changes here. Okay, this is all the same as before. Here is something different. Um, Before we talk through this, let's actually look at the ODE file. This is the ODE file. Okay, so let me change the file name here. Uh, so the ODE file, the first three elements are still omega xb, omega yb, omega zb. Okay, and then it's got 9 more elements 4 to 12 of state var, contains the rotation matrix Q. Okay, um, so 4 to 6 is the second column, first column, 7 to 9 is the second column, 10 to 12 is the third column. Okay, and so state var is the list. So you take the state var 4 to 12 and then reshape it into a 3 by 3 matrix so that we have Q as a matrix here so that things are convenient. So that's Q. And then we have, these are exactly the same as the Euler's equations that we used before, same equations that were simulated earlier. Okay. Um, okay, so these are the Euler's equation. Now we need to write a differential equation for Q itself, right? So recall we had this differential equation, Q dot equals omega Q um, times Q. Okay, Q versus Q. So this, let me call this omega matrix. It's a skew symmetric matrix times Q. Now we recall from our notes that this omega matrix is basically based on the angular velocity in the frame 0, the non-rotating frame, and given omega vector in B, omega vector in 0 is basically our B to O omega vector in B. And our B to O is just the rotation matrix Q as well. And we construct this big capital omega matrix, right? Let's take a look at that. Okay, this matrix, this differential equation is what we're trying to write here. That's this differential equation. And yeah, so to actually write that differential equation, we need to, oops, I seem to have deleted this, my mistake. to write this differential equation, we need to find omega matrix in terms of the omega vector in the zeroth frame. And to find that, we transform omega vector in the B frame to omega vector in the zeroth frame using the appropriate rotation matrix. Okay, so that's it. We have 3 equations and then 9 more equations. So this is now a matrix differential equation, but then we reshape q dot into a 9 by 1 vector again, so that this is 3 elements and then there's 9 more elements, so that this thing has 12 elements. Okay. In case you haven't used reshape, let me just do that here. Let's just define a matrix rand 3 comma 3 or something like that, and then if you go reshape 9 comma 1, sorry, reshape a of 9 comma 1, what that does is takes this first column, that's the first 3 elements, take the second column, that's the next 3 elements, take the third column, that's the next 3 elements. Okay, so we've reshaped a 3 by 3 matrix into a 9 by 1 matrix. That's what reshape is. Similarly, we can, if you call this B, if we call this B, then you can get A back by saying reshape of B 3 comma 3, and we get A back. We've taken this 9 by 1 matrix and then reshaped into a 3 by 3 matrix, where we take 3 elements at a time, and those things form columns of this new matrix. Okay, so elements are drawn column wise in this reshape operation by default. Okay, so that's about reshape. Okay, so we just saw this differential equation for Euler's equations plus the differential equations for the rotation matrix. Now we are all set to simulate the system. Let's just simulate this cell by cell. These are the moments of inertia, the principal moments, we should say more precisely. And then integration duration. Initial condition, so omega, like we're just using, let's say something like this, something close to 1, something close to exb, right? So omega is almost entirely along exb here. So we expect this to be stable, right? And let's make this relatively close to entirely being along exb. And then the Q matrix, the rotation matrix, we are using an identity matrix here. So to construct the state variable initial condition, we just go omega xb, omega yb, omega zb. And then for the rotation matrix, we use a 3 by 3 identity matrix here, but then reshape it into a 9 by 1 matrix so that this is a 12 by 1 array. And then we just call the ODE45, solve it. These are the same plots that we did in the previous version of the program, so I'm going to delete that. So we can leave that in, I suppose. Okay, so those are exactly the same as before. So just plotting the omegas in terms of time. And then now we want to do a simple animation. Okay, animation version 1. So these are the non-rotating axes. Okay, and we plot them, plot the fixed axes. And then we can make the line width of this. And then this is the loop that does the animation. Um, in this loop actually just plots the rotating body axis. So let's actually run until here. So let me run this, let me run this, let me run this, run, plot. This is what we saw before. This is mostly remaining close to 1, and then this is these two are mostly remaining close to 0. So if we want to go whilem -2 to 2, that it'll make it more clear what we're talking about here. This remains really close to 1, and this remains really close to 0. All those oscillations were relatively small compared to the mean. Okay, so, and then what does this look like? Let's actually run what this looks like. That's what that looks like. So this is the x-axis, y-axis, z-axis, and it looks like basically a pure rotation about the x-axis. Okay. It looks like a pure rotation about x-axis. Of course, it's not exactly a pure rotation about the x-axis, but it remains awfully close to a pure rotation about the x-axis. Okay, so I'm going to Control-C out of it. This little program here is a slightly fancier animation. What we did is actually drew the cuboid. The cuboid has 8 vertices. These are the 8 vertices based on the lengths of the sides. And then we can essentially apply Q, the rotation matrix, to each of those points. So P1 now is Q times the initial position of P1, so on and so forth. And then we can replot each of the points. And if we run that, this is what that will look like. Okay, so this is a pure rotation about the x-axis. It just remains a pure rotation about the x-axis for all time. Okay, or close to a pure rotation about the x-axis for all time. Okay, so that's about a stable axis, right? So the x-axis was a stable axis. Let's now change the initial conditions so as to be almost entirely. So let's make this a random number like we discussed. And then let's make it entirely about the z-axis. And that's what that looks like. So the body fixed axes rotate about basically their z-axis. And then the so-called fancier animation looks like this. Right, so it essentially remains close to a rotation about the z-axis. Now, what if we make it less close to a pure z rotation? What does that look like? You can sort of see, hopefully, that the oscillations, right? So you can see that the z-axis is sort of coming, is rotating about the original z-axis. You can actually make it more stark here. This kind of motion is sometimes called a precession, but in any case. Okay, so that's what that looks like. It still mostly remains close to being a rotation, largely about the z-axis. Okay, so that's, again, that's a rotation mostly above the z-axis. Now, let's actually make it along the unstable axis, the so-called unstable axis. Okay, so it's mostly along the y-axis and then a little bit along the x and the z-axis. Let's see what that looks like. So it's just rotating, rotating, and then does something really complicated, and then starts rotating with the negative of the original angular velocity, and then does something complicated, and then switches to the original angular velocity. Okay, so that's what we mean by unstable. Let me Control C out of it. And then if you look at this animation, it looks like this. And then the thing tumbles over and then rotates with the opposite angular velocity. You'll have to look really carefully to notice that it's the opposite. Um, okay, you can play with this simulation offline. Okay. Let's see if we can find a YouTube video quickly. So here you go, T handle in 0G. So this is a real motion. They gave it an initial velocity that is about the intermediate axis, and this is what the object does. Okay, it does basically the same thing that we saw in the animation. This is a slow motion version. So this will happen, of course, on Earth as well, on the surface of the Earth as well. For instance, if you did this exact same thing to an object and let it fall, it would fall down but do this thing. But of course, because there's air friction, these motions will slow down much more than in space. But in space as well, there is considerable air friction because these people are inside, have air inside the space station, of course. But on Earth, this would be a falling object, so it would lose energy much faster. In any case, yeah, so that's the phenomenon that we were talking about. Had they rotated this thing about, let me back up a little bit. Had they rotated it about, so they rotated it about this axis, had they rotated it about this axis or a perpendicular axis, sort of out of plane like this, it would have not done this weird thing. It would have continued to spin at that axis. Okay. So that's it for a simulation of a 3D rigid body object with three different moments of inertia, principal moments of inertia. And we started it off at initial rotations that were close to EXB, EYB, EZB respectively, and sort of found different results. Now, of course, you can start off with any old random initial condition, some random number. All three could be random numbers, and we just see what that looks like. The motion generally tends to be rather complicated. It's going a bit fast, but it's rather complicated, looking at least to the human eye. The important thing to remember is that even though the object has no external moments on it, the angular velocity does not remain a constant. The angular momentum remains a constant, but the angular velocity has the seemingly complex movement. Okay, so that was from essentially a random initial omega set of omegas. It does not remain constant. The omegas constantly change. Okay.